officially starting the show and the recording. Hi, folks. Happy Thursday. Happy lunch. Happy Snuggie. Whatever it takes, right? So folks have been asking me homework questions while we're waiting for everyone to roll in. So I'd like to open that opportunity up to everyone. How is homework going? It went? So I know I've been corresponding with folks over email as well. Is there anything that I can help with right now? And if the answer is no, because it's not due until next Wednesday, then I can live with that. But I just thought I'd ask. Yeah. Nothing in the chat?
For the last section,
yes.
We get the results from the previous questions and just compare them?
Yes. So it says, use only your previous results to answer the questions below. For model comparisons via likelihood ratio tests in which either ML or REML could be used, use REML, but then some of them would require ML, I will warn you as well. So yes, you should be using the values that you found up above to answer the question.
And that for the drop list as well, the question system.
Yes, okay. Yes, so refer to your values in answering all of the drop-down questions. You will see a pattern emerge, and that is the point, to actually see it in action.
I have a question about the same likelihood ratio.
Okay.
It's for the second one. I think that need to use ML, and my test statistics, the number is correct, and I use Excel to calculate the p-value, but I just can't get the p-value right. I wonder if the parameter should be 4, the difference of the parameter is 4, and my test statistic, the number is right.
Okay, which question are you on again?
It's the last question of that likelihood ratio test section.
59 and 60?
Yes. So my 59, the number is correct, but my 60, the p-value, I can't get it right.
Gotcha. Okay. So you should be using a regular likelihood ratio test, not the mixture version, because I'm trying to keep it simple. And I would double check your degrees of freedom that you're plugging into that, because that may be where the issue is. That would generate a different p-value with different degrees of freedom.
Okay.
Maybe
my understanding is wrong, but I think that's 4, the difference, right?
And I think it is not.
Oh, okay. So it's the degree of freedom. Okay.
So
thank you.
yeah, so give that some more thought, and then if you're still stuck, please send me an email or send one of the TAs an email, and we'll be happy to get you unstuck.
Okay, thank you.
Thanks for the question. All right. No? Okay, well then one other thing that I need to mention before I forget about it. So homework is due on Wednesday, not Monday, and we are getting kicked out of our classroom for comprehensive exams again next Thursday, so we will be on Zoom. It's in case that changes your plans for whether you want to come to campus that day or not, I want to let you know in advance. That should be the last time this semester though, but we'll see. All right, then our goal today is to try to wrap up Lecture 5 and Example 5, and potentially even start Lecture 6, although I'm not sure if that's going to happen or not. It'll take as long as it takes. Right? It does. That's what I say. All right, let me get this stuff out of here then. So in terms of strategy, I think I want to do the example first, make sure that we go through that, and then we can sort of fill in the pieces of the lecture slides that folks have questions about or that would be warranted by this. So I'm picking up on page 7 of example 5. This is when the multi-level part starts that we've been talking about. So the reference for this, by the way, thinking in terms of the pictures. So A, this is consistent with an empty means random intercept model. That's the first one that we have here. So this one is empty means, meaning no predictors. It has 3 parameters in total: fixed intercept, random intercept variance across people, which is level 1 or 2. Random, people, 2, yes. That means we also have E residual variance at level 1. Can I share my screen? Goodness, yes I can. Will I is a separate question. There we go. There we go. But at least I narrated. Do I get points for saying what slide I was on? Like, nah, not really. All right, so page 7, also flipping back and forth across slide 21 in lecture 5 with the pictures. So this model tells us how much of our total variability in our outcome is cross-sectional between person mean differences versus something to do with time at level 1. And we don't yet know whether we have change or fluctuation. We just know that there is some difference across time that we're observing to the extent that we have an interclass correlation that is less than 1. So this is, let's see, this one is Stata output. So I'm doing a couple of things here. I am saving the results of this model to do computations with. So this is a new thing that I'm introducing in this class and hopefully bringing into my other classes. Matrix creates a matrix of the results from this model, and I'm naming it empty RI. So this is analogous to what we would do in R to save an object. And so we got our fixed intercept here, the mean of the person means, that's 12. We have our random intercept variance here, so var constant is what that is called, and then variance of the residual is at level 1. This test right here, that is a likelihood ratio test. In Stata mixed, it is always a likelihood ratio test against a linear regression. So it has degrees of freedom of 0.1 here because it is treating this as a mixture chi-square distribution. So I have a little disclaimer about that down below. This is the thing, if you watched the video, that I said I've tried to care about, but I just can't. I just can't bring myself to. But Stata obeys it inconsistently depending on how you specify the model. So this test result would be compared to a chi-square distribution with 1 degrees of freedom if you're doing it the regular way, or a mixture with 0 and 1 if you're worried about the influence of boundaries. Either way, though, we would conclude that this model fits better than a standard linear regression. Said differently, we need the random intercept. Said differently, the intraclass correlation is significantly greater than 0. So 29% of all the variation in this example outcome is between persons, the rest is within. So I am showing here the results of the process of saving the results in this matrix here, the R table. I'm printing what I saved with the matrix list command. And the reason that I did that is because right here is a number that I'm going to need in order to compute pseudo R square. So that is the purpose of this. So what I did was go into this table here and say, all right, I need row 1, column 3, I'm going to need that number. I created a new programming variable. It's kind of like an object, but it's not in a data set. This is data code, by the way. And that number is actually the log of the standard deviation. So I had to turn it into a variance by squaring it and then exponentiating. So the number is that. So I'm verifying that it comes back. So I will use that number in deciding how much variance fixed time is going to explain in the next model, pseudo R square. So any questions on that so far? Okay, R folks, here is your corresponding code. I am using Elmer for this model here, and REML. And let's see, I think you've seen most of this stuff. So RunNova is likelihood ratio test when you're using Elmer. That's how you can test whether or not you need the random intercept variance. And in the same way that I saved the results of the analysis in Stata, I did the same thing here. So I took the variance components from this model, turned them into a data frame so that I could find them, and then went in and found the spot where the residual variance is and saved that as an object called empty resvar, residual variance from the empty model. That's my naming convention. Then we have fixed linear time random intercept. So how many things have I added relative to the first empty model? How many yellow things did I highlight? There we go. We'll ask it a different way. Yeah. So we have, this is new. So beta 1 multiplying time, and time has a TI subscript because it varies over occasions and persons. And right now, beta 1 is a placeholder or a container for how each person is eventually going to get their own linear slope, and right now it's just a fixed slope. So fixed means everybody gets the same, right? So this is literally like everybody gets this number. Everyone's slope is that. So that is consistent with this picture, B here, where we're allowing some kind of fixed time trend, but we're not yet allowing a random time trend. So to do that, we enter time, which has been centered so that time 0 was the first occasion. This is static code then to store the results of this model for a future likelihood ratio test, to store the full results of all the coefficients so that we can examine pseudo R-square. This will print minus 2 log likelihood because it defaults to printing just log likelihood instead. And then I'm writing code to generate predicted outcomes at each occasion. So this is the long, pedagogically informative way. Here is the easier way. So note that I am using this teal-looking thing here. That's a variable that I saved as to when the last occasion is. So that shows up in various places in my code so that I don't have to change it manually every single time. Saving the result, showing the saved results so I can figure out where the right terms are, creating a residual variance out of the saved results, and then computing pseudo R-square. So pseudo R-square in this model is how much the residual variance went down because we added a fixed effect at level 1. So whether or not there's change over time should help to reduce the ease because we're changing the slope of the line. And the version of this formula that is more intuitive is what it was in the previous model minus what it is now divided by what it was, but that can be simplified into the shorter version of the formula, 1 minus the variance from the model with time divided by the variance from the empty model instead. And here is the corresponding Elmer code, so time goes right there as a fixed effect. Here is the corresponding Elmer output. So in terms of random effects, something interesting happened. The residual variance went down, as we would expect, because we added a level 1 fixed effect. But that made the intercept variance go way up. That will happen because of this consequence right here. The variance that you get on your output is supposed to be corrected for the contribution from level 1 that would happen by chance. And that contribution is operationalized as residual variance divided by the number of level 1 occasions. So just a heads up that that will happen doesn't mean you did something wrong. Fixed effects then. What does my fixed intercept tell us? We'll start with the softballs. What is a fixed intercept in any class you've ever taken?
The mean of everything?
In this model, it's not everything anymore because we've added time.
Conditional.
Yeah, it's a conditional mean, and it's conditional on the predictors being 0. And this predictor is time, and time 0 is the first occasion. So 10.2 is the expected outcome at the first occasion, time 0. Time then, this is the slope. It's 1.72. Who's feeling brave?
So for every 1 unit change in time, we expect change in value of 1.7.
Exactly. For every unit change in time, y goes up by 1.7. And this is a generic data set, it's simulated data, so you can make up whatever units you want. But in reality, you would say for every day, for every week, for every month, like put the unit in there for the people. I would probably recommend trying to scale larger rather than smaller. So like change per day would be a very, very tiny number, whereas change per month would be, 30 times bigger. So if you have a scale where you're going to end up with 0, 0, 0, 0, 0 something, choosing a larger unit in time may help with that. Okay, so here are predicted outcomes according to this model. So here's the first occasion is 10.27, the second occasion is 11.99, so each of these differs by exactly that much. So it's a rate. Yes?
So, I know in the, whatever class it was, maybe cluster, we talked about rescaling the something time maybe. So how would you rescale it? Would you like multiply it to make sure it's not public zeros
Yeah, I would convert it from like days to weeks or months or however, whatever conversion you would need to do. So it's all, I mean, it would depend on what kind you need, but yeah, I would do the conversion.
And that's when you like are originally cleaning your variables.
Yes, that would be like a pre-processing step. Yeah, question?
And if we didn't center the time, that would change the interpretations of the first of the fixed effects, but does not affect the interpretations of the variances.
Ah, great question. So whether or not we've centered time in this model will only affect one thing. Which intercept?
This one.
This one. Judge's ruling, I'm sorry, I see the word intercept in two different places. This one. Which one?
Fixed
No, this is a point. This is because this is something that's unique to multi-level models. So the fixed intercept is always conditional on the predictors having a zero value in a certain spot. So the fixed intercept would move around if you center time differently. In this model, because time does not yet have a random slope, the variances would be the same. ...
Would it be the same if you rescale your units? So is the person variance reported in units of the outcome variable, or is it standardized?
The random intercept variance would not, it should not be affected by your scaling of time.
Okay.
The time slope will be, though,
Okay.
because this is the remaining variability at level 1 and at level 2. So then in terms of how much variance was explained, what I'm doing is comparing the residual variance from the first model that had no predictors in it, so it was 7.055, to the residual variance after adding time, and that number was 2. So that's quite a bit of a reduction. It works out to be, there's the 2, about 0.69. So 69% of the residual variance was explained by including a fixed effect of linear time. Question in the back?
Lisa, can you repeat please the interpretation of the fixed intercept?
The fixed intercept is always the expected outcome when predictors are 0. In this context, it's the expected outcome when time is 0, and based on how I centered it, it's the first occasion.
Yeah, to me, what is weird is that in the formula, we can see that the fixed intercept is at level 2, is like a cluster thing.
Mm-hmm.
So I was thinking that that was the predicted outcome across clusters, but you are right that conditional on all the set of predictors being 0. So how can that be possible? Why the fixed intercept is at level 2 and not at level 1?
So question is, why is the intercept considered a level 2 parameter? So fixed effects always go into the level 2 notation. It's a question of then what they end up multiplying. And in these models, the intercept is considered level 2 because it has a random part with it. This one, see, this is where I get the distinction of what you call a fixed effect is one of those things actually people disagree about. Like to me, the fixed slope of time is a level 1 effect because time is a level 1 variable. But if you look at where it goes like in the notation, it looks like level 2.
Yeah, because what I can see there is that the fixed intercept is helping us to predict the cluster-specific intercept.
Person-specific in this class.
Sorry, yes, person-specific intercept.
Yeah, we cannot
However,
cross the streams.
At the same time, we know that if we recenter time at level 1, the fixed intercept will change.
Yes.
So to me, that's like weird sometimes.
Mm-hmm. Yeah, yes, it is weird, and people see it differently depending on. So I think of it as like you can think of these all as being in the level 2 notation, but it's like what do they end up doing in the composite model?
Okay, great, thank you.
So, sure. All right, other questions? Okay. So, about 70% of the reasons why people were off their line is because we drew one flat line. If we make it a tilted line, then that explains some of the level 1 residual variance, and doing that increases the random intercept variance. Now the new one. I don't think we actually got through this one in class, did we? So now it's time. So random linear model. This one has How many new parameters, and don't say one? 2. Yeah, what are they? Zoomers, I'm watching the chat too. You can play.
Variance and the covariance.
Hey, variance of the random linear slopes. So that idea right there, U1, has a variance associated with it. And what's not shown in this notation is that the U's get to be correlated. So there's a covariance. And actually, I should have yellowed this because this is new to the Stata code as well. That is what makes it happen. Stata defaults to having random effects that are uncorrelated. Yeah. So does SAS, by the way. R is the only package I've seen that doesn't have that as a default. SPSS does as well. So in adding to the code, time is over here now without a C dot in front of it because it yells at you if you put that here. So note it's in both places. It stays as a fixed effect over here, and it's added as a random effect over here. So that's not redundant. It's doing two different things. And adding covariance unstructured refers to the structure of the G matrix specifically. So G is always, always going to be unstructured forever and ever, amen. No other structure makes sense for G. The reason is that G is level 1 or level 2? 2. So G contains random effect variances and covariances. They get to be whatever they want. Like there's no structure that would make sense for that otherwise. The R matrix is still independent, which is why we can use Elmer for these models in R. So after we control for individual differences in intercept and now linear change over time, we say the residuals are uncorrelated across time with constant variance. All of the reason for differences in variance and covariance are supposed to be in the G matrix via the random effects. So now, fixed effects are the same. This is balanced data, but they changed their interpretation a little bit. The time slope is now the average time slope of the people slopes, but these are balanced complete data, so it works out to be the same number. This is Stata output, by the way. So now we have the 3 terms. That's your G matrix right there. Var time is random linear slope variance. Var const is random intercept variance, and then this is the covariance between the two, and then residual variance is in the bottom here. So do we know if this is significant or not? Did adding this and this help? These are variances, right? What do we need to do? Anytime we want to mess around with the model for the variance and see if we need stuff. Likelihood ratio test. Now you might be tempted to be like, hey, is that it? Can I just use this one? There's a very subtle clue in here as to why the answer is no. And it's the 3. This is testing whether you need a G matrix at all. All 3 random effect variances, 2 variances and 1 covariance, 3 elements in G. So that is not going to answer that question. We have to do a separate likelihood ratio test to answer that question. So I asked for some post-estimation commands, SStat recovariance, re-level person ID correlation. I don't have this stuff memorized. There's no way I would have come up with that. This is the G-core version of the matrix. So this is the correlation between the intercepts and the slopes. If I want the V matrix, it's right here. Remember what V is? Put back together again, yep. If you take the level 2 G matrix and combine it with the level 1 R matrix, V is the result. Now this is an interesting result. This is what the model predicts. It predicts variances that increase over time, and it predicts covariances that change over time, and here's the correlation version. So this is another pattern. It was built with the same logic as we looked at in the previous unit, autoregressives or topolitzes or all the things. This is a pattern, but it's built via continuous time instead of discrete time. So I wanted to show you as part of the lecture where that came from. Now, I'm going to re-answer your question, Ahmed, about what would change. So in the previous model, the intercept variance was 4.1. After adding a random linear time slope variance, it is now 2.2. It changed. Because when you add a fixed linear time slope, the fixed intercept is conditional on its value being 0. When you add a random linear time slope, the random intercept is also conditional on the predictor being 0. It works the exact same way. So this intercept variance is no longer the mean across time. It's individual differences in the predicted outcome specifically at time 0. Because we are in pictures C or D, in which you would come to a different estimate as to what the intercept variance is if you looked at it here versus here versus here versus here. So it's at time 0 specifically. So it will change in terms of the variance components once you add random things. So the fixed intercept is conditional on all predictors that have fixed slopes being 0. The random intercept is conditional on all predictors that have random slopes being 0. They're in parallel. Yep. So just as the fixed intercept is conditional on all the predictors that have fixed effects being 0, the random intercept is conditional on all the predictors that have random slopes being 0. And they will change. And so it does matter in these models whether 0 is a plausible value. So I once helped someone to troubleshoot a very complicated multi-level structural equation model in the context of cognitive aging, and the model wouldn't converge. She had done everything right. I looked at the code and just was like, okay, what's wrong with this? And then it occurred to me, she had age as a predictor. These are older adults. She did not center age. So the random intercept variance was trying to figure out the variance across newborns as measured by people who are 80. It couldn't do it. Lo and behold, once you subtract 80, converges like that. So lack of centering can actually break these models. I've seen it happen. So I would keep that in mind when you're thinking about scaling your predictors. All right, we have the predicted means again. That is our predicted V correlation matrix. We'll show you how I got that in just a minute. And then a few more things. Here's my likelihood ratio test. So I'm using LR test and Stata to do this. The model that has more parameters comes first. The model that has fewer comes second. And the result of that says the test statistic of 48. So yeah, we would say we definitely need the random slope, which is good since that's how I simulated the data. So now I'm computing a bunch of stuff. Effect size. If we added a random slope variance to the model, do we need to compute some sort of pseudo R-square for that? What do you think? If we add a random slope, are we explaining variance? No, what are we doing instead? Partitioning. Yeah, we're turning a 2-pile model into a 3-pile model. So some of what we were calling E has been reallocated to level 2 slope differences. Why were you off your line? Oh, you need your own line. Okay, I get it. So it's explained in the sense that we know that it has something to do with individual differences in change, but it's unexplained still in that we don't know why some people grow faster and some people grow slower. So it's still error conceptually. So instead of pseudo R-squares, I have two things. One is, we talked about, I think on Tuesday, a random effect confidence interval where the center is the fixed effect, and then the plus or minus part is essentially 2 standard deviations according to the corresponding variance component. So I have one for the intercept here, I have one for the linear slope here. The numbers came from the output above. So at time 0, people are expected to range from about 7 to 13. In terms of their rate of change, they're expected to range from negative 0.15 all the way up to 3. So on average, as given by the fixed slope 1.7, people are growing by 1.7 per unit time. But the variance around it is such that some people are actually predicted to decline instead. That's how I would explain that. The others are reliability coefficients. So intercept reliability, or ICC2 as it is more often called, using the intercept variance, residual variance, and the number of level 1 occasions. The intercept is fairly reliable. So individual differences at time 0, that's the reliability coefficient that goes with it, 0.93. Slope reliability is computed similarly, except that we also have to rescale for what a unit is in the predictor. So this number right here, the 1.26, that's the variance of time as a predictor. That's where that came from. And I have code that will get that and save that for you in my examples. So those are the things that I would report to try to convey like how variable my people are in this sample. I feel like these are the kinds of numbers like that you could give to like a clinician in terms of like this range, right? What is the expected variability at this age or at this point in time? And then how variable are the slopes? Like these are numbers that have direct meaning in the context of the scale of the variables. So then in here, I'm saving the pieces, all the values that went into these computations, and then doing the computations this way. So theoretically, you should be able to use this code and repurpose it without changing anything, or without changing very much, at least. So I'm trying to do better than like separate spreadsheets for hand entering things, because that is not reproducible. But I do have spreadsheets if you want to use those instead. I don't really care. So there's all the corresponding code that computed all of that stuff. In Elmer, the output is structured differently. So it does not give you a covariance in the output, it gives you a correlation. However, if you need to get a covariance, you can compute one with the standard formula for going back and forth across correlations and covariances. So there was nothing I could find that directly would give me a V matrix using Elmer output. So I started Googling, and I found this. I'm not even going to try to explain it, but it's essentially doing the matrix multiplication that would involve in building the V matrix, and I can show you that in terms of equations in just a second. So after all of this work, and by the way, this is another thing that should work regardless, it's general code, and this is the V matrix, and this is V core. And then I generated some predictions so that I could make some pictures, I think. All right. Then we have RANOVA, likelihood ratio test. Saw that before. And then building the same confidence intervals and reliability coefficients as that. So where did this V matrix pattern come from is the question. Like, how did we get to that? I'd like to show you. And unfortunately, it's going to require some matrices. Okay, so slide 26, lecture 5 here. This is where that V matrix came from. So when you add random slopes to a model, what you are saying is that people differ from each other in more than one way. The default is that we have a random intercept for mean differences. Once we add random slopes, that's another kind of difference. So in terms of the ingredients that are going to build V, level 2G is always unstructured. So we have random intercept variance first, random slope variance second, and then the off diagonal is the covariance. And this is a symmetric matrix, so there's really only 3 terms in here that you need to pay attention to. The R matrix at level 1 is diagonal, or independent. And this is the only kind that Elmer allows, by the way. So you will see me switch back and forth whenever I need to put something else in here, like in the next couple example models. But this model says that the E variance is constant across time, and the E residuals have no covariance. Now that, if you look at this, it's like, wait a minute, is that reasonable for longitudinal data? Well, if all I had was this matrix all by itself, no. But what it's saying is that the E's are independent because all of the reasons for their dependency, for their correlation, are over here in G. So if your model is properly specified, then we have the same assumptions as standard linear regression. E is homogeneous, independent, constant variance, independent, and normally distributed in these models. Yep. So how do we combine these two things then? I'm not great at matrix operations, but I can tell you, you can't stick together things that are different dimensions very easily.
You need the Z matrix.
Yeah, we need the Z matrix. So, different slopes implies changing variance across time. Here's how that happens. So I have a derivation in the book. You can follow this if you want to, but I'll skip right to the highlights. The end. So the predicted variance at each occasion is due to the random intercept, due to the residual variance. That was what we had in a compound symmetry model. The part that's highlighted in blue is the new part. It's time squared times the random slope variance plus 2 times time times the covariance. So the point of the story is that the variance is predicted to change based on what occasion it is. It's changing in this function, though, as a function of the slope variance and the covariance that we added. So in the previous models, when we had different variances, it was like homogeneous or heterogeneous. And if it was heterogeneous, then you had like 7 variances instead of 1 or something like that. This is creating heterogeneity, but it's doing it through 2 parameters as a continuous function. So this model could tell me what the predicted variance is at any occasion. It's a function, and it's actually a parabola. It's a quadratic function. Likewise, predicted covariance between 2 occasions is now a function of which 2 occasions they are. So if time A and time B, the covariance between them is a function of their specific time values as well as the random slope variance and the covariance, in addition to the constant part, which was the random intercept. So that's one way that we can explain the pattern that you see in V. The variance is changing quadratically over time, and the covariance is changing in this pattern. Now, to get to where that is, though, I got to do matrices. Yes, please, stop me from doing matrices. Lord. Gladly, yeah.
So the blue box equation in 29,
Yep.
is that the same equation as the blue box in 28, just with something filled in? Like,
Nope.
I don't know what the difference between those is.
So 28 is the predicted variance at each occasion, so the diagonal. 29 is the off-diagonal covariances. But
Will
this...
you read slides? What? Absurd.
Well, you know, to be fair, like there's a lot of stuff here, so yeah. No, the point of the story is that each of these is a function of the 2 new parameters and then which specific time it is. So the function can extrapolate to any occasion. It doesn't have a different variance for time 1 than for time 2 than for time 3. So it's very flexible in terms of building this pattern.
And this happens pairwise, so we have to switch between occasions if we want to get all covariance.
Well, these are the ingredients that build that, but the matrix equation will give you V in one fell swoop. I'm trying to like inch our way there. So this is the version that you would see if you looked in a stat textbook that describes these models. And I changed the notation to match the scalar version, but usually this would be like x beta right here. But since I'm using gamma for fixed effects, I stuck with gamma. So these are the pieces as to how we end up with a V matrix. So this is for one person, 4 occasions. X contains the predictors that have fixed effects. So the first column is for the fixed intercept. The second column is for linear time. Then we have the fixed effects themselves. Then we have this thing called Z. This is a matrix that holds the predictors that have random effects. So they're 2 different spots because not everything that has a fixed slope necessarily needs a random slope to go with it. So we have an intercept, and then we have the second column for which particular time values a person has. We have their corresponding random effects, and then we have their e's. So Z here is the magic that allows us to put R and G together into V. And it looks like this. So we have Z, which is, again, one person. These are the values of the predictors in the model that have random effects. So this person has 4 occasions, so they have 4 ones for their intercept. These are their time values. Z transpose is that on its side. And these wrap around G to get it to be the right 4x4 dimension to be able to add to R. And then the pattern, that if you figure out what the diagonal looks like, it's that blue box formula, and the off diagonals are all built with this formula here. So G is level 2, R is level 1, and Z controls how G operates in a person's data, which occasions they have and how many. So let's say if I have data for 2 people, what is actually happening in the software is that V is a ginormous matrix for everyone and everything. And it has this block diagonal pattern. So this is what it would look like for 2 people. Here's the first person. They came at times 0, 1, 2, and 3. The second person came at different times. The zeros here and here are because we say people are independent. That part hasn't changed. So at the highest level of these models, you're still assuming independent observations. What if my second person didn't come back on the last occasion? Could that happen? Sure, it could. Or they skipped, let's see, they skipped the third occasion. All right, well, their little pocket is a 3x3 instead of a 4x4. So that is how missing data is handled. You are building a custom V matrix that has the dimensions as how many occasions you actually contributed. And unbalanced time is being handled because we can fill in whatever time values we need. These random effect variances and covariances build a function that allows the variance to change in a time-specific pattern. Ba-dunk. So the end of the story is that we're still back to patterns. Compound symmetry is random intercept only. Unstructured is everything gets to be what it wants. Random slopes models are using fewer parameters than unstructured, but allowing the pattern to better match what's actually in the data. So if I have my random linear time model, how many parameters is that? Count them up.
6.
We get back to the equation many pages ago, yep. So 2 fixed effects, and then I have 1 E variance at level 1. I have 1 U0 variance at level 2, another U1 variance at level 2, and the covariance that's not in the equation, so 6 is right. Now if I had 20 occasions, how many parameters does this model take? 6. If I had 1,000,000 occasions, how many parameters does this model take? 6. So it's relatively parsimonious. However, it assumes linear change, which once you get past 3 or 4 occasions, you're probably going to need some bendiness. So that's the next unit. It's all about that stuff.
So
Yes.
I know the sample size here is 25 persons, right? In example 5. So when should we advise the one who's consulted that we need more cases?
Question was, is 25 people enough? Not really. I think it depends in part on what you're most interested in, but if you want to get stable, decent estimates of your random effect variances, 25 is not going to be enough. 50-ish and past that, but it depends on how large the signal is to detect, of course.
But we have a higher reliability, like 93 and 85 in this case. So this might be like something good with
Well,
this sample, I mean.
So yes, the reliability of the intercept is relatively high, but the question is, how good of an estimate of that variance that went into the formula is it? That's what we don't know. Like if you redid the study with 25 people and over again, how wiggly would those variance estimates be? Pretty wiggly. So I think that's more the issue, is do you trust what you're getting back?
So what parts of the output should we refer to if we want to collect more data? The variance?
Well, so the variance is a necessary precursor to being able to predict that variance. So if you're interested in fixed effects of people characteristics, then you essentially have power of 25. So if you look at it that way, like that's not good enough. And how many more you would need would depend on what the minimum detectable effect size is that you want. So that would be the way I look at it. It's like go to a power table and be like, well, for 25 people, you can detect an R of 0.8. But if you want an R of 0.3, then you need a whole lot more. And the same is true for level 1. Like in this example, we have 4 occasions and 25 people, which is 100. But do we really have 100 observations? Effectively, no. So this is something we talk more about in a clustered data context, but to the extent that you have correlation among the occasions from the same person, you don't have independent information. So to compute power for level 1 terms, you need to be able to anticipate what is known as a design effect, which is based on interclass correlation and the number of level 1 observations per level 2 unit. So you'd have to correct for the dependency to get an effective sample size with which to judge your power. Question?
Is it like the same formula that you use basically as with any sort of clustered thing? It's just your level 1 is different. It's timed out.
Yes, yep. So the question was, is the formula for computing effective sample size the same as it is in clustered? Yes, it is. And chapter 13, I think, of my book, the last chapter, has power analysis and Excel calculators and stuff for you in there as well. So that's something that I have to do quite a bit. You need to be able to anticipate an interclass correlation, and you need to anticipate how many level 1 units per level 2 to be able to do that. So how many occasions per person here? How many people per school in clustered land? Yep. So in this data set, our power for level 1, based on 100 observations, would be somewhere between power for 100, which would happen if we had an interclass correlation of exactly 0, meaning the occasions have nothing to do with each other from the same person, then it's really like 100 separate things. Or worst case scenario would be power for 25. That would be consistent with an interclass correlation of 1. So somewhere between those two extremes is what your actual effective sample size would be. Yes. All right, what do I want to do? Oh, I know what I wanted to do. This. This is an assumption. Diagonal R. What if the residuals are still correlated after we add our random effects?
You can't use Elmer.
We can't use Elmer, that's correct. But could we test something? Like, could we throw an AR1 correlation in here and see if that helps? Sure we could. Yeah. And actually, I was helping with the project this past summer where they had 30 observations. And the model was like fixed quadratic, random linear, but we needed an AR1 correlation because residuals for occasions next to each other were still had an additional relationship. So the more occasions you get, the more likely you're going to need something else in R. And that is what I wanted to show you next. So we can test that kind of assumption as well. But we have to switch software to do it. Okay, so this one is, do we need something else in R is the question. This is page 13. Should have yellowed this. Here is the new part. We changed independent to AR1. Why don't I yellow that right now? There we go. So that adds how many new parameters? If I change my R matrix to be autoregressive?
One more.
Just one more. And if I had 7,000 occasions, how many more parameters would that be? One more. Yes, same idea. So the rest of this is the same, just changing this request, and that will change the corresponding patterns that show up in my V matrix. In R, Elmer will not do this. So I had to switch back to the NLME package, which has the function LME. So it's structured a little bit differently. We have a fixed part and we have a random part, and then we have this correlation option that is not available otherwise. So the new parameter is this right here. My AR1 correlation was estimated at 0.03. So this is one instance in which I think you could probably get away with staring at a p-value for it, given that it's a correlation that has a null hypothesis of 0 as a reasonable thing. But we'll do a likelihood ratio test anyway. So this is the R matrix that parameter built. This is the R, or did I show the? No, I didn't show R core. So this is the number that would get squared for lag 2, cubed for lag 3, and so on. That translates into a predicted covariance that is the same over time right here. And it looks like probably don't need it. Yes, indeed, my likelihood ratio test value is 0.002. So, and the p-value is almost 1. So AR1 is not necessary in this model. I also tried one more, Toeplitz. Lag1 correlation. That is here. It's not available as a built-in structure within LME. I'm sure you could figure it out, but I haven't done that yet. So I tried one of those. That is adding a lag1 covariance that was estimated at 0.012. So again, very small. Corresponding V matrices there and corresponding likelihood ratio test there. So no. One other thing that you could test is whether the variances on the diagonal of R need to be homogeneous or heterogeneous. If you estimate these models in structural equation modeling software, the default is that they're heterogeneous instead. I have seen issues, though, in trying to allow that because what the random slope variance is trying to do is make the variance heterogeneous over time. So if you let the residuals also have heterogeneous variance, there's a sense in which that's redundant, and the two could fight against each other. So I've seen results go haywire when you're trying to allow both to vary at the same time. So I tend not to do that. Within SEM, you can tell with local misfit indices whether or not you might need like one to be different than the others or something like that, which would be a reasonable thing to do. But I typically don't try heterogeneous residual variance models. All right, there. We got through the part of example 5 I wanted to. And here is SEM code. And if you're like, no, then it's fine. But these are the same thing. All right, I think we hit almost everything that I wanted to say about that. So questions? What am I forgetting? What do you want to hear more about or differently?
I'm interested in Ahmed's question. So do we need different sample sizes for these different methods, or is it like just anytime we add one random effect, we need more people? Like if we add multiple random effects, does that quadruple the amount of people we need, or like how do we figure that out?
Great question. So how do you figure out sample size? I don't think it's as straightforward as like some multiplier of the number of random slope variances. I don't think that would work. As a general principle, the more things that have random slopes in your model, the more likely it is to have convergence problems, and the more people you would need to try to figure that out. I think in general, you can say that if you're interested in level 1 fixed effects, like you need a lot of level 1 units. If you're interested in level 2 fixed effects, you need a lot of level 2. Anything that has to do with the random effect variance, though, you need a lot of people to be able to get a decent estimate of that. But then you also, like if it's a random slope for change over time, you would still want to have as many occasions as possible so that that slope itself is estimated well, and then the variance around it is estimated well. So it's difficult to anticipate because it all fits together. And I have programs like to do power analyses for these things, I use simulation. And those are tricky because you have to be able to anticipate values for all of these things. So what I typically do in practice is work backwards. So Vladimir has experience with this. Is this fun, Vladimir, to figure out power?
Yeah,
It is not, no. Yeah, I've tortured both of them earlier this year with that. So it doesn't matter what the numbers are. Let's say that I have a variance of 10 for my outcome, okay? It doesn't matter what it is. First thing I need to figure out is interclass correlation. So if I say I think an interclass correlation of 0.3 is reasonable for these data, okay, that tells me that my intercept variance is going to be how much? We'll turn this into an interactive thing. Yeah, let me get a spreadsheet out to keep track of this. So we're not doing math in our heads. No good can come of that. Okay, so we have total y variance. Okay, I'm going to say that that's 10. If I have my inter-class correlation of 0.3, then my U0 variance, come on, has to be what? I'll put them both up in here. Residual variance, if the inter-class correlation is 0.3,
Oh,
that's the proportion of
0.3,
variance
sorry.
that's which one?
0.3.
3. That means this one has to be 7. Okay, so I'm halfway there. Now this formula is for slope reliability given a known amount of slope variance. Reverse engineer it. I think my slope reliability is going to be 0.8. Then I can use this and work backwards to figure out what slope variance would be consistent with that, of 0.8. And the other thing that I need to know is the variance of the predictor. Let's call that 1. Who cares? It's x, doesn't matter. And the level 1 sample size. So you can come up with reasonable guesses for your variance components just by anchoring to something and then figuring out the rest. And I do have material I can send anyone if you're interested in this. There's also about 1,000 R packages that do this at this point when they'll take this kind of input.
All of these doesn't account for missing values for sure.
Yeah, so this is starting by simulating complete data. That could be something else you could do is poke holes in it systematically, right, to see how bad it gets. Mm-hmm. All right. Let's talk names for a second. Fixed side, random side. Because there's a hierarchy here. Come on. Here we go. So if I have just an intercept that's fixed here and nothing that's random, what kind of model is that? Empty means without any random effects? That's called regression, right? There's nothing there yet, so I would say this is like linear regression. Empty. Empty means. If I add a random intercept, what would I call that? Yeah, empty means random intercept is what I call that, to be very specific. But unconditional or empty is the general term you'll see. Unconditional means model. Starting put. All right. If I add fixed linear time, but nothing to the random side, I would call that fixed linear random intercept to differentiate the two. So then, this fixed intercept goes with this random intercept. This one doesn't go with anything. So that means this fixed intercept is conditional on time 0 because of that, but the random intercept is not. If I add the corresponding random linear slope, then what would I call it? So here's two choices. You could say fixed linear, random linear, but in reality you don't have to do that because there's a hierarchy here. If you have a random effect, you have to have the corresponding fixed effect underneath it because it is the center that the random effects are deviating around. So it is assumed, if I were to say random linear, that I have the fixed linear in there, which is why when it gets asynchronous, I make that differentiation. So what if I had a model that looked like, go down here, I have an intercept, I have an intercept, and I have linear. What would I call that? Wrong! Because it breaks the rule. So things are conditional sort of this way. Like the intercept is conditional on all the predictors that have fixed slopes on the fixed side. The random intercept is conditional on all the predictors that have random slopes on this side. And you have to have a fixed effect if you have a corresponding random effect, because it's the middle. So together, back to the formulas, together, there we go. There. We have fixed plus random, fixed plus random. That is going to hold. You're going to see that the rest of the semester and the rest of your multi-level lives. So if you see the U by itself without the corresponding fixed effect, that's saying it's exactly 0. That will cause estimation problems. So the two work together to figure out what the total slope would be. Fixed is the part that everybody gets the same. Random is the part that you get that's separate. Same thing on the intercept side. So where we're headed then, can you guess what will happen next week? Because I was right, we're not going to get started on that. Let's say I want to make the line bendy. Can I do that? What's an easy way to make a line bendy? Square it. So where's that going to go? Yeah, I'm going to have a new beta 2 attached to times squared. And if I have a new beta 2 in level 1, I need to put it in level 2 as well. And do you think people need their own kind of bendy? Maybe. How can I do that? U2. Yes, gamma 2O plus U2. So yeah, same principles. The only catch is how many occasions you need to be able to actually pull that off. It turns out for a random quadratic, which is the next model we'll practice in homework after this one, it is 4 occasions at a minimum for that to be identified. You need 3 to identify a random linear model. 2 is insufficient. Okay. Anything else that you want to talk or ask questions about before we call this unit done and our week done? Yes, please.
Could you just quickly review the slope reliability, what that means, like what the interpretation of that value is?
Yes. I think it's, let me find it again. Further back. I don't know where it is. Vladimir, do you have that slide memorized too? Like, I know what I'm looking for. There it is, for 38. Yes. So conceptually, it is telling you, like, relative to the variability that is over time, not just like cross-sectional, how much of it is because of slope variance versus E variance around the slopes. So if you picture like the lines, you know, cutting through all the dots, it's like, are the dots tightly clustered around the line, like the line fits really well, or are they really spread out around the line? So the ingredients, slope variance, residual variance, level 1 sample size, and then the variance of the predictor that it's the slope for, because the number has to have a unit attached to it.
Yeah, and you talked about like linear one, for example, that you can get that somehow in your code, but I'm still confused exactly what that like means, the sigma squared out of 1.
Oh.
What?
This is the variance of the predictor that it's the random slope for. So the variance of time as a column in your data set in this context, for instance.
But for that specific like individual or like line.
Yes, so the x-axis, whatever variable that is, it's that variance. So I wrote it in a way that's more generic so that you can extrapolate to other contexts. But in this context, it would be the variance of the time predictor itself that you would need to go find and enter into the formula. Level 1n, it would be average sample size per person if it varies across people. So this might be another one where you could plug in like a range of values to see what the range of slope reliability might be if you have unbalanced data in that regard. So the thing about this, though, that I do want to emphasize is reliability we're used to thinking about as kind of a black or white concept. Like, we want high reliability, right? That's good. Well, what if I have a really low slope reliability? That could happen. And it could happen for reasons that aren't a problem. Maybe people are just really homogeneous. Maybe kids don't vary in how much they change in this particular sample. Well, then the slope variance is going to be very small. And it will look like it's not reliable, but it's just a consequence of how this is defined. There's just not a lot of signal. But in a different sample with different people, there might be more variability and change. So we should be able to increase it by adding more level 1 observations. That much is true. Okay, did that help? Okay. Any other questions? Zoomer's been quiet today. They're like, we're always quiet, we're on mute. All right, then how about I give you 5 extra minutes of your life back? Are we okay with that? All right, I will be sitting up here anyway since I'm ready for my next class, so if you want to ask homework questions or anything, let me know. Otherwise, have good weekends. Thanks for being here. Bye, Zoomers.